In this video, I'll be continuing my series on computer systems by taking a brief look at virtual machines. This is a Module 9 topic, so it's just a very quick look to get the basic idea of what virtual machines are and how they work. Now, what a virtual machine is virtualization technology enables a single PC or server to simultaneously run multiple operating systems or multiple sessions of a single operating system. So we don't have to dual boot things. We don't have to have the operating system tied to the hardware anymore. We can virtualize the whole thing and run many instances of different operating systems on a single host. The machine with virtualization software can host numerous applications, including those that run on different operating systems, and do it all on a single platform. This can help us to avoid wasting resources. The host OS can support a number of virtual machines, each of which has the characteristics of a particular operating system. So the nice thing about this is we can consolidate things, right? We can use one host and run multiple operating systems using the resources that each instance needs so that we don't have to waste extra memory and computing capacity, right? Processor capacity, disk capacity. That we may have had to do before when we were tied to a single operating system on a single physical host. Now, the solution that enables virtualization is called a virtual machine monitor, VMM, or a hypervisor. So the way this works is we have shared hardware down at the bottom, then we have our virtual machine manager running on that hardware, and then we can have as many virtual machines as we have resources for running their own applications and processes running on top of that virtual machine manager. So this allows, again, I was talking about utilizing physical servers more efficiently. We can do something called virtual machine consolidation. So instead of, if I have 6 different operating systems or 6 different applications that I need to run on separate systems, instead of having to do 6 physical servers, I can have a single virtualization host, right? One physical server that runs all 6 of those instances as virtual machines. And that would be an example of a 6-to-1 consolidation ratio. Now we got some different approaches to virtualization, right? A VM, it's just a software construct, and it's going to mimic the characteristics of a physical server. We'll configure it to virtualize some number of processes, some amount of RAM, some amount of storage resources. Once we create the VM, we can power it on just like a physical server, load it up with an operating system, software solutions, whatever we can do on a regular physical server, we can do on this virtual machine. Now, unlike a physical server, this virtual server only sees the resources it's been configured with, right? Not all the resources of the physical host itself. So if I have a system with 16 cores and 16 gigabytes of RAM, right, I can configure a couple of different VMs on there, and maybe one of them only sees 2 cores and 2 gigabytes of RAM. The other one might see 4 cores and 8 gigabytes of RAM. Each individual virtual machine only knows what it's been configured to see. The hypervisor facilitates the translation and I/O from the virtual machine to the physical server devices and then back again to the correct virtual machine. So that's what our hypervisor does for us. It just manages all these different instances of virtual machines on our physical system. And virtual machines are made up at the most basic level. They're just made up of files. We have a configuration file that describes the attributes of the virtual machine, contains the definition, how many virtual processors, how much RAM, etc., and so on. Also describes the storage that the VM can access. So when the VM's powered on or instantiated, additional files are created for logging and memory paging, other functions that we need when we're running an operating system. Now, since the VMs are already files, copying them produces not only a backup of all the data, but it's also a copy of the entire server, which means this is so wonderful. I can just copy a virtual machine from one physical host to another. I don't have to rebuild. I don't have to reconfigure. As long as I'm using the same hypervisor, or at least a hypervisor that's compatible with the format of virtual machine that I'm using, I can just copy them and move them around at will. So we've got a couple different types. We have a type 1 virtual machine manager, where we have The shared hardware, and then we just have the VMM, right? The hypervisor runs directly on the hardware. The VMM runs in what we call on the metal. Then we have the various virtual machines that run on top of the VMM. In a Type 2 virtual machine monitor, we actually have the shared hardware that has its own host operating system, and then the virtual machine monitor runs as an application within that host operating system. So rather than running the VMM right on the metal, we're going to have a host operating system. This can be Windows or Linux, whatever you want it to be. Then we install the virtual machine monitor as an application, and after that takes care of organizing and running our virtual machines. Now, another concept that we want to be aware of when we're talking about virtual machines is paravirtualization. This is software-assisted virtualization that uses specialized APIs to link virtual machines with the hypervisor to optimize performance. The operating system in the virtual machine, Linux, Microsoft, Mac OS, doesn't matter, has specialized paravirtualization support as part of the kernel, as well as specific drivers that allow that operating system and hypervisor to work together more efficiently with the overhead of the hypervisor translations. Now, this has been offered as part of a whole bunch of different general Linux distributions since 2008. So this is a common thing, right? And we hear more and more about it. As time goes on, more and more things end up getting run on virtual machines because it's just so much more cost effective than having every single operating system instance tied to its own physical server. Now, we do have to deal with some processor issues. In a virtual environment, there's two main strategies for providing processor resources. We can emulate a chip as software and provide access just to that resource. QEMU, an Android emulator, and the Android SDK use this kind of approach, right? We're just going to emulate a chip, right? Emulate a virtual processor that the virtual machine has access to. The other option is to provide segments of processing time on physical processors to the virtualization hosts, right? So we accomplish the same thing, but we do it in a different way. We slice up the resources of the physical processor rather than emulating a separate soft processor. And this is how most virtualization hypervisors offer processor resources to their guests. Another concept that we want to be kind of aware of is Ring 0. Native operating systems manage hardware by acting as an intermediary between application code and the hardware. One key function of that is to help prevent malicious or accidental system calls from disrupting the applications or the operating system itself. Now, protection rings describe the levels of access or privilege inside a computer system, and a lot of operating systems and processor architectures take advantage of that as a security model, right? We're going to keep ourselves secure by keeping these protection rings intact so that only certain things, certain processes with certain privileges can actually access certain resources. Now, when we talk about these models, the most trusted layer is called Ring 0. And that's where the operating system kernel works and what can interact directly with the hardware, right? That's the stuff that gets right down to interact directly with the hardware. It's the most basic, low level. So that's the one that has, of course, the most power. This is where we can really mess things up. And hypervisors run in Ring 0 so that they can control hardware access for all the virtual machines that they host. Now, when we talk about memory, right, we're going to have each virtual machine will have its own virtual memory space, and we'll also have the host with all the actual physical memory, and we can do something called page sharing, where each virtual memory basically just maps to a page in the virtual memory maps to a page in the physical memory, and that makes things a little easier as well. Since hypervisor manages page sharing, the virtual machine is not really aware of what's happening in the physical system, right? The virtual machine, again, we always want to keep in mind that the operating system on the virtual machine, as far as it's concerned, it's running on its own physical hardware, right? We can assume that we can just treat a virtual machine like it's a physical system. So one thing that we can do for memory management is something called ballooning. The hypervisor activates something called a balloon driver that virtually inflates and presses the guest operating system to flush pages out to disk. Once those pages are cleared, the balloon driver deflates, and the hypervisor can use physical memory for other VMs. So this is something that the hypervisor can get in there and apply some policy to what's going on in the virtual machine to make sure that it's utilizing the physical resources of the host system as efficiently as possible. And what this allows us to do is have something called memory overcommit, which is the capability to allocate more memory than physically exists on a host. So I could have multiple virtual machines running, and if I add up all of the virtual memory of all those virtual machines, that can actually be higher than the amount of physical memory on the host, because we have this ability to kind of do some tricks and organize things so that we can swap things in and out of virtual disk space and stuff, so that the hypervisor can control things and we can actually sort of effectively get more resources than we even have physically available when we add up all of our virtual machines. Obviously, when we start ballooning and paging, we're going to have some performance issues, but that can be handled in the design of the overall system. Now, when we talk about network as well, what we're going to have is in the virtual machine, we have our operating system and we have a network driver, right? We have a network interface control driver, which attaches to an emulated device in the hypervisor, which has its own NIC driver, which actually accesses the network interface card on the physical server, which takes us back out to the network. So this is another way we're emulating things. But we can end up passing all of this information from our virtual machine out to the actual physical host and get our data in and out of our physical host and get things to the virtual machine properly. So what we can do is basically in the hypervisor, we can emulate a network interface card for each virtual machine or each NIC in a virtual machine that we're running, so that we can keep things all straight. And we can use network address translation to ensure that things get to the appropriate virtual machine and even the appropriate interface on the appropriate virtual machine. We could even run our network in something called bridged mode, where the emulated NIC is kind of passed all the way through to the physical NIC on the host system, and the virtual machine's network interface gets treated as though it's directly plugged into the outside network, so we can even pass things straight through that way. Now, we've talked about managing processor resources and memory resources and communications resources. Now, and that network communication, of course, is part of I/O, but let's talk a little more generally about input-output management when we're dealing with virtual machines. One advantage of virtualizing the I/O path is that we can have hardware independence by abstracting vendor-specific drivers to more generalized versions that run on the hypervisor. So what that enables is live migrations, which is one of the virtualization's greatest availability strengths, right? The sharing of aggregate resources such as network paths. This makes life a whole lot easier. If my virtual machines are only looking for drivers, I/O drivers, that are going to get to the emulated versions of the I/O paths on the hypervisor, this is another thing that allows me to move them around like crazy, right? Now, the hypervisor ends up managing all the traffic, right? And that requires some processor overhead. But what this allows us to do is if I've got two different physical systems and they have very, very different I/O devices attached to them that wouldn't normally be compatible, that would require different drivers, that's okay. Because if I've got a hypervisor that understands that I can install all those drivers on the individual physical systems, the hypervisor connects to those, and then what the virtual machines connect to are generalized device drivers that are emulated in the hypervisor. That allows me to take a virtual machine and copy it from one system to another, even if those systems have completely different hardware. Right? This is another huge benefit that allows me to migrate virtual machines around like crazy without having to care about the different pieces of hardware and the different kinds of device drivers that may be needed for all of those different physical hosts.